Hello, in this video, I'm going to show how to use Python in conjunction with the singular value decomposition to take an image and compress it. Now, the image I've selected is something I found on the internet. This is a copyright-free image, and we're going to use the singular value decomposition to compress it to various degrees in Python. So the first thing we need to do is, well, actually, before getting started, let me just show you the output. So here's something that's compressed very much so. Here's something even more. And so we're going to explain how to basically code this up. Okay, so first, how do we get started in Python? Well, we need to find a Python editor, kernel, and so forth. And in this course, we've been using Sage Math. That's built on top of Python. And so if we want to create a Python file in kernel, we have to go to new. And typically in this course, we've been using Sage Math when creating a new file. But now what you want to do is create or click on Jupyter Notebook. And right now, we haven't selected the kernel, or essentially the programming language or interpreter that we want. And so we want to select Python 3. It might be over here, or it might be listed down here, like so. And so click on this. All right, so that's how to get started. And here you'll type in your Python commands. And then if you hit the run command, or sorry, this button, or hit Shift Enter, it'll give you the output. Now, I've already typed up beforehand, and the links should be in the description to my code. So there's two different files. One is where I've just written up all the code, and it's very short, just I don't know, 20, 30 lines here. And then there's another file over here that goes slowly in more of an exploratory manner to what all the commands mean. Okay, so let's start with that. So the first line of input is these two lines here, and there's something you'll see in many Python scripts involving linear algebra, particularly import numpy as NP. So numpy stands for numerical Python, and it's a it's something that contains the code for numerical procedures, like numerical linear algebra procedures, like the singular value decomposition, the determinant. And then every time we want to refer to that package, instead of writing the word numpy, we're just going to abbreviate NP. That's a fairly standard abbreviation. Okay, and then the first one here, matplotlib.pyplot, that's a package or module that contains code for how to take an image and turn it into a matrix. Okay, so basically we can just, to some extent, ignore these or treat these as black boxes. That's sort of built-in code. And then we go to line 2 of input. After you enter this line, you do want to hit the run command. I've already kind of done that before. Okay, so then I want to upload a picture. Now, I actually need to, well, I've already done that, but one would need to, you would need to do that ahead of time or now. And that is go to CoCalc, and in that directory where you have your project, or wherever this new file that you created, this new Python file that you created, upload. So how do you upload an image? Here's the upload button, and then you upload whatever image you have or want. Desktop, I think, yeah, I click on the dog picture here and choose for upload. I've already uploaded it, so I'm not going to click on this button right now, but you can see that the dog picture is uploaded here. Okay, so once we have this picture uploaded into the directory where this Python file, notice that the extension for this Python file is IPYNB, so it's a Python notebook, sort of an interactive place where you can type in Python code, as well as then hit run and see immediately the output. That's what a Python notebook is. Okay, anyway, moving on to line, this, I guess, input number 2 here. It says the plt.imread. So what this is we're using this plt library. I mean, it's actually, the library is called matplotlib.pyplot, and I'm just abbreviating it to plt. And in that package, there's a built-in command called image or imread that you give it the file name, and it reads in that image file and stores it. What it stores it as will be turns into a matrix, as we'll see. But right now, we just assign that to the variable name that I made up called mypic. Okay, and then plt has a command called imshow, and that will show the picture that you just read in. And again, I've already hit run before, and here we see this picture that we're going to compress to varying degrees. Okay, that's a picture I found on the internet, not unfortunately my doc, but okay. So then what kind of object is this mypic? Well, so I type in mypic, and again, this is not something that's part of the minimal code that you need to compress an image, but here I'm just exploring what is going on. What kind of thing is this mypic? And then when I ask Python for its type by this command, it says it's basically an array. An array is kind of like a matrix. It's technically a different data type than a matrix in Python, but it's like a list of lists of lists. That's essentially what an array is. Very flexible. Okay, and then this command np.shape, the shape command method applied to this mypic tells you how big is this array, and it gives 3 components here, 3 coordinates, and this tells us that it's a 3-dimensional array that just is it's pretty huge array. It's got 1399 in this first component, and what that means is this is 1399. It's a list of 1399 matrices. Each matrix, which is huge itself, it's 1920 rows by 3 columns, as we'll see. So when we ask Python what does the display mypic, it spits out this thing, and it's an array. And what this says here, it's got it's a list of lists of lists essentially, and 1399. Oh, let me just back up a bit. This image here, where are these numbers, huge numbers, coming from? This image has 1399 pixels in one direction and 1920 pixels in the other direction. So the total number of pixels is the product of these 2 numbers, and that's a huge number. And then each pixel is storing, or the data associated to each pixel, I should say, is storing 3 numbers. The RGB, or red, green, and brown coordinates of the color of that pixel. And we'll talk about that shortly. Anyway, so this is what this picture is being stored as. It's being stored as a 3-dimensional array, basically a souped up matrix. And each entry is not just the number, but 3 numbers, a triple. And these numbers are all between 0 and 255. And that's because the numbers associated to the RGB coordinates follow that requirement. Okay, so let's pick a particular entry in this huge 3-dimensional array. So to access that, you go mypic 0, 0, and it spits out this triple. And this corresponds to the 0, 0 position in your picture. And let's go where that is. That's out here. This is the 0 and yeah. And so this pixel here is a certain color. And if you zoom in, you can kind of maybe see that it's some sort of gray or white or something. And then if you go to look up on a different website, where was this color? What is this color exactly? This is what its RGB coordinates are. What is it exactly? You can just type it into Google and RGB, and it will, yeah. What we have here is this particular website. The background color here, this grayish color, shows you what color this triple of numbers, 211, 213, 212, corresponds to. Okay, so then let's move on. Yeah, so there's a triple of numbers, not just a single number associated with each pixel. And we want to separate these numbers because when applying singular value decomposition, we can apply it to a matrix of each entry corresponds to a single number. Whereas right now, each entry, if we were to view this matrix as this image as a huge matrix, each pixel would correspond or contain the data of 3 numbers. And so I'm going to separate out the red, the blue, or green, and blue components. And so that's what this command here, myPickRed, or not command, but this line, myPickRed does, is it says in this 3-dimensional array, pick out the entries starting at 0, which is where Python starts counting from. So this is really in the first of each triple. So what we see here is when I call myPickRed, I get a list of 211, 213, 215. And if you look at what this array myPick was, that's exactly these first few numbers. Okay, so we've extracted out the first, or the red component. That's why I was labeling this array. Now it's a 2-dimensional array, or just a regular type of matrix. And what is its size or dimension? The command for that is in the np package, the method shape, apply it to this object myPickRed, and you get the dimensions of the picture. And so that's maybe not a surprise. Each pixel, this is how many pixels there are, and each pixel has a coordinate like so. And okay, so then we do the same thing for myPickBlue, where we pick out the second number in each triple. And again, because Python starts counting at 0, the second number corresponds to the 1, and then myPickGreen is a 2. Now I just noticed that I think in the RGB, the green corresponds to the second number, and the blue corresponds to the first number, the third number, but that's fine. I mean, this is not going to cause any problems. Simply because I've just made this error consistently throughout, and it's really a naming issue. I should have, instead of calling myPickBlue, I should have called this myPickGreen. But I've stayed consistent throughout. And so to the computer, the myPickBlue matrix really records the green component. But anyway, okay. So now finally here is the application of the singular value decomposition. It's, we've got this NP, the numerical Python package. Then within that package, there's a module called linear algebra that further has linear algebra programs like the singular value decomposition. And so then we call that and apply this to this matrix, my pick red. Technically, it's not a matrix, but an array. And okay, and so then when we call np.linearalgebra.svd, we get a triple. We get this an array or two-dimensional array that I'm calling or assigning the variable u sub red. Then in Python, we don't get a diagonal type of matrix, but instead we just get the list of singular values. And then finally, V is going to be the orthogonal matrix, V transpose, that we've seen in class. Similarly, U is going to be the orthogonal matrix U that we've seen in class. Okay, and so again, this is a way of telling Python, this is the output. The output is a list of 3 things, and assign U sub red to be the first item in that list, S sub red to be the second item in the list, and so forth. Anyway, so then let's ask Python what is U sub red, S sub red, and V sub red. And here we see it. So U sub red is this first array. It's a 2-dimensional array. It's it's maybe a little hard to make out anything from these numbers, but okay. And then what is S sub red? It's if you look down here, it's not quite an array, a 2-dimensional array, but rather a 1-dimensional array or list. It's just a list of numbers, 2 times 10 to the 5th. So that's 20,000, I think. And so that's the first singular value. And then another, 2.4 times 10 to the 4th. I think that's 20,000. The 10 to the 5th is probably 200,000. But okay, some huge number. And, but yeah, it drops by a factor, a factor of 10. This 10 to the 5th versus the second singular value is 10 to the 4th. And that's what how we've ordered the singular values. That the highest one is first. That contributes the most, in some sense, to the image. Okay, and then there's this ... and then we end up with 5 times 10 to the 0. That's 10 to the 0 is 1. So essentially, the very last singular value is 5. So we went from singular values of 200,000 to down to the very last one is 5. And this is the idea behind compression, is you don't have to take all these singular values, just take, the first maybe 20, the first 50, the first 100, and we'll see the different effect each of those numbers has on the image. Okay, and then finally, here's this matrix V. Okay, let's ask for, how are these, these matrix, how do these matrices look like? It's a little hard to tell from the printout here. And so for that, I have this line here that I'm applying the shape method, that again is the method that tells the size of something, to some arbitrary element x. And what is x? Well, I'm going to let x be either u red, s red, or v red. So x runs through this list. This is like list comprehension in Python. Make a new list out of these np.shape calls. And so then what it tells me here is this matrix U is a square matrix of 1399 by 1399. And that's exactly what the singular value decomposition says. If A is our m by n matrix, then U is an m by m. Similarly, down here, V is an n by n. And then usually in the singular value decomposition, you have a m by n. But here in Python, the SVD method does not give a diagonal type of matrix. It gives just the list of singular values, and that's okay. We'll have to fix that and turn those singular values into a matrix or array along the with the singular values along the diagonal. Okay, then let's look at what S dot red is. These are the singular values. These are again the eigenvalues of A transpose A. Well, the square roots of the eigenvalues A transpose A. Okay, and then here's, it's just simply a list of numbers. And so we've got to turn that into a matrix consisting of diagonal entries given by these singular values in order to compute the singular value decomposition, and from there the spectral decomposition. Okay, so here's this command. It's a built-in command, or within the NP package, there's a diag command that turns a list into a matrix whose diagonal entries are the elements of that list. So the first element, first singular value was 200,000 roughly, and there we have it. Then it's followed by a bunch of zeros. And then the second row of the matrix starts with the 0 and then goes to 2.4 times 10 to the fourth. Now it looks like, it might seem that this is the third row, not the second row, this row right here, but the first row is actually where this matrix, where this open square bracket begins and this other open square bracket ends. So that entirely is the first row of our matrix. Okay, so it takes up 2 rows in the output. But anyway, okay, so then what's the shape of this diagonal matrix that we created? It's, okay, something like this. Okay, so then, now in the singular value decomposition, the diagonal matrix has size, the size of the original matrix, which was 1399 by 1920. Here we're getting by with not adding in some extra zeros, because when we do the matrix multiplication, those are going to make everything disappear. So that's why this number, second number, is not, it's okay that's not 19 by 20. Anyway, so we do the same thing. So this was just all for the red, the matrix encoding the red components of each pixel. We do the same thing to the blue and the green. So here again is the call to the, the call to the singular value decomposition. And then we get these resulting matrices out of the, and again, I've run all this ahead of time, so that's why it seems like we're not doing anything. But every time you enter or type this up and just hit run, and these computation of the singular value, I can actually just hit run again right now. And you'll see that that takes up, right now the CPU is, what was 0 momentarily ago, but it takes a few moments to compute the singular value. These are huge matrices, and it takes, I don't know, 10 seconds or so. And then, okay, so it seems to have finished. Anyway, okay, so now here's where now that we have the singular value decomposition, we can decide how much we want to extract from it. How many, maybe the first 5 singular values and the first 5 columns of U and the first 5 rows of V, or V transpose. And that's what I've done in input 16. I'm going to say, let's take the first 5. So I'm setting rank to be that number. And then what I want to store as compress underscore red is the product of the first 5 columns of U. That's what this command here is, of U sub red. This just dot or colon says that could be anything. The colon operator is to indicate range, like from, and if you enter nothing, that means it's the 0 starting point and ending right 1 less than the range. Sorry, the 1 less than the rank is what this second part here is telling it, is you can let anything in the first position, so that's how we encode or capture all the column, because the row could be anything. So that's going to capture this first column. And then the columns are restricted by, the indices of the columns are restricted by the number in here. Okay, then this @ symbol, that's matrix multiplication in Python. So if you write regular star, you either might get an error or might get the wrong answer because regular multiplication or star in Python, it does the stupid multiplication of multiplying each entry by the corresponding entry, just like you would do for addition. That works. But for multiplication, that's not how matrix multiplication works. So you want to use the @ symbol to multiply this matrix here, U sub red with this diagonal matrix we computed, and then multiply that by V sub red, and this time we want the rows. And we're gonna store that result as compress.red. So to tie back what we just did to the theory we've discussed or will discuss, is this here is the singular value decomposition. It's what we found. We've got a somewhat diagonal type of matrix, then an orthogonal matrix here and an orthogonal matrix here. And the idea behind the spectral decomposition is there's a lot of information in here, but because the singular values are arranged so that this one is the largest one and then they're arranged in decreasing order, that we can often get by just selecting a few of the largest singular values there, and then the corresponding row columns there and the corresponding rows here. And in that, when we multiply just those columns, just those singular values, and just those rows to cook up this new matrix A sub r, and that's this procedure, what that turns out to be is this thing here. That's exactly what we did in that line, is we chose r, the rank, to be something like 5. And so we're multiplying the matrix consisting of the first 5 columns here, the first 5 singular values there, and the first 5 rows there. And we're going to get a new matrix. And that will be very close approximation to the original matrix of the image that we started off with, well, technically the red components of that image. Now, to see a video that explains this a little bit better, or much better actually, Google Luis Serrano, SVD, and you'll come up with this video that he made explaining singular value decomposition. So I highly encourage you to look at that video. He does a great job with smaller matrices. Right now we've got huge 1900 by 1300 matrices, and with all these decimal numbers, so it's a little hard to maybe see what's going on. Okay, so then we've got this compressed matrix consisting of the red, and what we need to do is turn all these decimal numbers to integers, because that's how when we convert back into the image, we need those colors. Remember, these numbers are between 0 and 255, but the integers are the ones that can correspond to colors. So the next line does just that. It takes this compressed red matrix, and this command I had to look up, as type int, just rounds them down to integers and tells Python that it's the variable type is the integers, not a float, and that will enable us to be able to turn these numbers back into an image later on. Okay, so here's this compressed red matrix, and then I've asked Python, what does it look like? And here's the entries. Okay, so it's some sort of matrix, and each matrix or each element corresponds to the red value of the corresponding pixel. So this very first entry that's in the 0, 0 position, that's the red component of the very first, or the upper leftmost pixel. Okay, so now that was the idea for rank 5. What I want to do is make a built-in or user-defined, sorry, not built-in, user-defined command to where I give you the rank. So we'll see what happens if I give you a rank 5 matrix. This is actually what the output or the compressed image looks like, very blurry. You can kind of see that there's something in the middle here, but maybe it's a dog, but who knows. And then if we compress rank 20, that would be taking 20 singular values, the first 20 columns, the first 20 singular values, the first 20 rows of V, then we get a little bit of a better image. And then if we go to 100, even more crisper. And then if you do 250, it's even better. Okay, so what I'm going to explain next is how to build or define this compress function that I wrote and made up, essentially. Okay, so here's how to define a function in Python. You type in def, the name of the function, and the things you are giving as input, and then followed by a colon. And then you need to leave an indent here that will tell Python that everything below here that's been indented is part of this compress function that you were writing. Okay, and then essentially we just do what we did above for our 3 matrices, red, blue, and green. And so that's what these 3 lines here are. I went through above what happens with the compressed red. Again, we're basically doing matrix multiplication. This is the singular value decomposition, but we're, instead of taking all the rows or columns or singular values, we're just taking the first whatever rank is. Okay. All right, so now we've got these 3 compressed matrices corresponding to the red, the blue, and the green, and we want to put them back into a 3-dimensional array. And the command to do that, I had to look up actually, is the stack command. And that takes these 3 matrices or 3 2-dimensional arrays, compressed red, compressed blue, compressed green. I've maintained consistency with the order that the matrix I'm calling compressed blue is in the middle, even though RGB, the G is in the middle, but so anyway. Okay, so then the stack command, and then the axis is 2. What does axis 2 means? Well, there's a few ways you can take these 2-dimensional arrays and put them into a 3-dimensional array. And the way we want is axis equals 2. So don't worry too much about that. You can, Google the stack and npstack.python to figure out more details about this. Okay, so then we've got this compressed array. We're basically essentially done down here. Let me just skip over the next 3 lines for a moment. And then what we're going to do is plot this compressed matrix. This is a 3D matrix. In other words, roughly speaking, each entry corresponds to a pixel, and not only just a single number associated with that pixel, but the triple of RGB coordinates associated to that pixel. Okay, and so then when the image IMShow takes a matrix and spits out what image does it correspond to. A matrix or 3-dimensional array of RGB values. Okay, I mean, you can throw in any matrix and it'll assume that you're giving the grayscale and it'll print out some image. Okay, so then let me move back to how to compute this compression ratio. So in Luis's video, he explains why when you only take the rank number of, say rank is 5, take 5 columns and the first 5 singular values and the first 5 rows, those make up just a very small fraction of all the entries of the singular value decomposition. And how many entries? Well, it's going to be 5 times the number of entries in the rows. So back up here, rows, comma, columns, basically extracts out how big is our picture. We've got 1399 rows and 1920 columns. So that's what these numbers are going to be in this particular image. And then Luis explains why that the number of actual numbers that we need in the compressed data is given by this rank times the quantity rows plus columns plus 1. Basically, we've got rank number of rows, rank number of columns, and a rank number of singular values. That's exactly where this formula here is coming from. And then we divide that. We want to find out what is the compression ratio. How does that number compare to the total amount of entries in an M by N matrix or in the image file or image matrix? And that is just the number of rows times the number of columns. That's the total number of numbers associated to the matrix or array corresponding to the image. Now, technically, it's 3 times that because each pixel has not just one number associated to it, but 3. But because there's the 3 in the denominator and then the 3 in the numerator, those are going to cancel out. So I left it. I left that off. Okay, so then we're going to print the compression. Okay, now finally we can get to running this thing. Okay, so when I evaluate compress 5, I mean I've already done so, but if you're doing it for the first time, you would type that and hit Shift Enter. Let me at risk of okay, yeah, and that created this image, and this compression percent is 0.61. So that's using a very tiny amount of the original data, and obviously, we've lost a bunch of information. This is very blurry. Then when we jump to compress 20, it's better. The picture is much, well, fairly better than, at least you can tell it's a dog this time, but it's still fairly blurry. Let me zoom in a bit. And we're compressing at 2.4%. And then if you choose compress 100, it's something like this. Well, yeah, much better, but still, fairly somewhat blurry. And then what I've done is you can create an interactive widget, if you will, that creates a slider that allows you to slide. So let me just do something like this. And then it will, yeah, unfortunately, I kind of, instead of sliding it over, I should have just hit one spot on this interval. Okay, but now if we're instead of 200 or 20 or 100, we use 394. Now the image, well, we're only still compressing at 48% as opposed to 100% of the original data, but the image is quite sharp. Okay, so that's what this image compression using singular value decomposition is about.